Bismillahirrahmanirrahim. Assalamualaikum students. Welcome to Electronics. I am Madam Rosmin Azwin Abdul Rahim. As usual, to get the blessing from Allah Subhanahu Wa Taala, let's go through this one hadith. Abu Hurairah radhiyallahu anhu reported, the Messenger of Allah sallallahu alaihi wasallam said, "He who does not acquire knowledge with the sole intention of seeking the pleasure of Allah, but for worldly gain, will not smell the fragrance of Jannah on the day of resurrection." Riwayat from Abu Dawud. Okay, this hadith actually is very important to remind us the sole purpose of our knowledge seeking. Okay, we should always clear our intention. We should always know that why we are seeking knowledge, because at the end of the day it's for Allah's sake. At the end of the day is the pathway for us to enter the Jannah. Okay, yes, we can hope for the worldly gain, but don't forget the main intention should be for the sake of Allah. Now let's move to chapter 2, Semiconductor Materials and Diodes. In this video, we are going to cover chapter 2C, which consists of two subtopics, which are the Diode DC Analysis as well as the Diode DC load line. Okay, DC Analysis and DC load line. Okay, for the first subtopic, which is on Diode DC Analysis, you should know that in doing DC analysis, diode can be represented with three models. Okay, the first one is called the ideal model, okay, where V gamma equals 0 volt. The second one is piecewise linear model, where we have V gamma equals 0.7 volt, and piecewise linear model, where V gamma equals 0.7 as well as having a series resistance to it. Now let's have a look on the first model, which is the ideal diode. Okay, so as you can see from this IV characteristic of the ideal diode, as you know, the positive region here actually represents the forward bias condition, and the negative voltage here actually represent the reverse bias condition. So for ideal diode, automatically for positive voltage, as you can see here, there will be current, where the current is a vertical line here for the positive region, forward bias, and for negative region, okay, for the negative voltage here, which represents reverse bias, as you can see here, the current is 0. What does it mean? It means that under reverse bias, always our diode is represented with an open circuit, because to represent the current equals to 0. Current is 0, so the diode is represented with an open circuit. Okay, but when we discuss about forward bias, in this case the diode is replaced with short circuit. Okay, so when the diode is under forward bias, it is represented with short circuit. When the diode is under reverse bias, it is represented with an open circuit. For the second model, the piecewise linear model with V gamma value, as you can see the IV characteristic of the diode, for the forward bias, okay, for the positive region here, you can see that initially the current is 0, right? But at the point of V gamma, which is the turn on voltage, then only you are going to get a value of current, meaning to say then only at this time the diode will be on. Okay, and for reverse bias, as you can see the negative voltage area here, okay, still the same, where the current is 0, indicating the diode is off. The diode is not conducting. Okay, so to represent these IV characteristics for second model, whenever we are having diode under forward bias condition, under conducting state, okay, so this diode can be represented with V gamma, okay, with a value of V gamma. It depends on the question, okay, but normally it's around 0.65 to 0.7 volt for silicon diode. Okay, so how do you represent the V gamma? It depends on the terminal of the diode. So as you can see here, positive side here and negative side here, right? Okay, so as you can see here, we are having positive side here and negative polarity there for the V gamma. And talking about the open circuit, I mean on the reverse bias, it can be replaced with open circuit, similar like the ideal diode. Okay, talking about the third model, which is the piecewise linear model, but this time, as you can see from the IV characteristics, instead of having just a vertical line, you see the line now is having a slope. Okay, meaning to say, once the diode is on, okay, whenever the diode voltage is increasing, the diode current is also increasing. Okay, then this IV characteristic can be represented by this model, where when diode is forward bias, okay, so in the circuit we can represent that diode with a V gamma. Okay, but in series to the V gamma, we have a resistor in series to it with a value of RF. Okay, this is how do we represent the diode for the third model, the piecewise linear model, where we are having V gamma as well as RF. Okay, for the reverse bias, it's just the same for the three models. Okay, where under reverse bias condition, the diode is replaced with open circuit. Okay, the question is, why do we need for these three models, okay, if we can just use the ideal diode equation for our DC analysis? Okay, because before this we have discussed this ideal diode equation, remember, where ID is equal to IS exponential VD over VT minus 1. Okay, so if you can find ID from this equation, obviously we can find for the rest of the circuit parameters, right? Then to see why do we need for these three models, let's have a look on this example. Okay, we have a simple diode circuit where this diode is connected to BPS. Okay, but in series to it we are having one resistor, okay, 2 kilo ohm. Then from here, since we are having one closed loop here, actually we can do KVL equation, right? Minus VPS plus IDR plus VD equals 0. So from that, you can get this KVL equation. Okay, then you may rearrange, you get this ID equals VPS over R minus VD over R from the same KVL equation. Okay, now let's have a look if we were to solve this DC analysis, the same circuit that we see just now, using the ideal diode equation. Okay, so let's say in this case we are supposed to find for the diode voltage, which is VD, and the diode current, which is ID. Okay, the IS value is given. Then let's say, remember just now we do KVL equation, we are saying VPS equals IDR plus VD. Okay, so this is VPS equals R, and this is the ID. Okay, the ID equation, remember the ideal diode equation, times the R. Okay, this is the R value, right? Okay, and plus VD. Okay, so now we are using the ideal diode equation in this KVL equation. Okay, so once we substitute everything, we can see there will be one unknown, which is VD. Okay, one unknown, which is VD. But the problem is this VD is in the form of VD and as well as in the form of this exponential, meaning to say it's not that straightforward for you to solve for it to find for VD. Okay, there are two methods that you can do. One, you can do some sort of trial and error, substitute VD and find this VD whether it match the values, or another method, you need to do some kind of iteration method. Okay, you put all the data into the software or the MATLAB, then you do some kind of iteration, then eventually you are going to get, oh, VD is equal to 0.619 volt in this case. Then obviously once you get the VD, substitute into the KVL equation, you are going to suppose you are going to get ID, which is 2.19 milliampere. Okay, this is a diode DC analysis. A few examples. Okay, the same thing here. You can do the consider the three models. Okay, that we can do in diode DC analysis. Then for this case, since V gamma is given as 0.7 volt, we know that now we are considering the second model. Remember the piecewise linear model with V gamma value of 0.7 volt. Okay, then since we know we are talking about second model, then the next thing we need to do is we need to find I and V naught. I is the current, V naught is the output voltage. Okay, but first thing first, if you are given a circuit like this, actually these two circuits are separate circuits, meaning these are two different examples, okay, that you need to solve to find for the current as well as the output voltage. Okay, so let's have a look for the first circuit. First thing first, what you need to do is you need to complete the circuit, because as you know here, this node is connected to positive 5 volt and this another node is connected to negative 5 volt. Okay, so what you have to do is you have to draw the complete circuit. It means that this node is connected to positive 5, meaning this node is connected to positive polarity of 5 volt, while the negative one is grounded. Okay, the negative one is grounded. Okay, so this is 5 volt. This is 5 volt. Okay, then the same thing goes to here. This node is connected to negative 5. What does it mean? It means that this node is connected to negative polarity of 5 volt, while the positive one is grounded. The positive one is grounded. Okay, so since we are having both ground and ground at the same level, we can connect them together. Okay, so now the value here it is not negative 5 anymore, because negative is already represented with the negative polarity here. So the value of this voltage becomes 5 volt only. Okay, then from here actually you can have one closed loop. Remember, can you see the closed loop here, right? Then you can do the KVL equation, but this time around, since we are having we are having diode under forward bias condition, this diode can be replaced with V gamma. Remember the second model, this diode can be replaced with V gamma value. So from here you can do the KVL equation accordingly, where negative 5 plus I times 20k plus V gamma plus I times 20k minus 5 equals 0. That should be the KVL equation. I repeat, negative 5 and plus I times 20k, because the voltage drop across this resistor, plus V gamma, which is 0.7 volt, plus I times 20k, which is the voltage drop across this resistor, minus 5, which is the voltage here, equals 0. That should be the KVL equation. If you solve for this, you are going to get the I value, the current. Okay, then for the V naught, as you can see here, V naught is the output voltage where it is connected to this node, and meaning the other node is connected to ground. Okay, the other node is ground. The other node is ground, meaning the V naught here actually is the summation of this voltage plus this voltage. You got my point? V naught is actually the summation of the voltage across this 20k plus the voltage which is negative 5 here. That should be our V naught. Okay, so I leave these two examples to you to do your revision. Then we are going to discuss in class. For example 2 is just the same thing, where you need to consider for the model. Okay, in this case again V gamma equals 0.7 volt, meaning we are considering second model. Okay, piecewise linear model with V gamma equals 0.7. Okay, so as we can see here from the circuit, obviously the diode is forward bias, right? Positive goes to positive, negative goes to negative. So this diode can be replaced, can be represented with V gamma, right? Okay, so the same thing like we discussed before this, simply we can do KVL here. Okay, we can do KVL to find for the ID value, minus VPS plus IDR plus 0.7 equals 0. So from there you are going to get ID. Then this is another equation related to the same circuit. If VPS is now changed to 8 volt, what must be the value of R to get ID equal to part A? So it's just the same thing, just kind of reverse approach, but this one I'll leave it to you to solve for this. Now we come to the second subtopic, which is the DC load line for diode circuit. Okay, what does it mean with DC load line? DC load line is actually another approach of getting ID as well as the VD value, but now we are using a graphical method. Okay, so from there from the KVL equation, actually we are supposed to get a linear line equation, which is ID versus VD, to obtain the whatever parameters which are needed. Okay, so for example, in this case, remember we have, for the diode, we always have the ID characteristic, okay, where ID versus VD, then you have this kind of curve, right? So the y-axis is actually ID, and the x-axis is actually the VD, right? Okay, so in this case, we want to get the KVL equation in the form of ID versus VD, because we are going to plot on this IV curve. Okay, so as we can see from this KVL equation for a basic diode circuit, where VS or VPS, the supply voltage, is given by IDR plus VD. Remember the basic KVL equation. Okay, if we rearrange this equation, we are supposed to get this in this form, right? This is the form of load line equation, because as we can see from the graph here, okay, it is ID versus VD. So now ID become the y-axis, okay, then obviously VD is the x-axis. Okay, then we have M here, which is -1/R, as well as the C, which is Vs/R. Okay, so actually from this linear line equation, we are supposed to get a straight line here, right, with a value of C equals to Vs/R. Okay, here is one example on how do we do the load line analysis. Okay, for this basic diode circuit, okay, as you can see here, we have the power supply, the resistor, and the diode, right? Okay, so if we do the KVL equation for this diode circuit, okay, we are supposed to get this KVL equation, right? But then we rearrange to get in this form, because remember, we want to fit into this IV characteristics, where ID would be the y-axis and VD will be the x-axis. Okay, so that's why we are having in this form. Okay, so this equation here in this form actually is called as load line equation. Okay, if you are asked to come out with a load line equation, it should be in this form. Okay, then from this load line equation, actually what we can do here, remember, to draw a straight line we need to have at least 2 points, right? Okay, so what you can do here from this load line equation, maybe first to get the first point, we may consider ID equals 0. So if ID equals 0, automatically we know, oh, VD should be equals to 5, okay, which is represented at this point. ID 0, VD equals 5. Okay, then for the second points, let's consider VD equals 0. Then you can see VD 0, ID equals 5/2. Okay, so when VD 0, ID equals 5/2, which is 2.5. Okay, so you have 2 points. Okay, then you can connect them together. Then the intersection between the straight line with the IV curve of the diode should give us the value of the Q point. It should give us the value of this Q point. So from this intersection, you can see here, this should be the value of our ID, and this should be the value of our VD. And these two values, ID and VD, it should be the same if we do the KVL analysis. I mean, we do the calculation to calculate using the three models. Remember, it should be the same value of ID and VD. Then talking about load line analysis, sometimes it's not that straightforward where circuit is given, then you need to plot the load line graph, something like that. It can be also in some kind of reverse approach, okay, as you can see from this example. Okay, in this example the circuit is given and even the Q point and the IV characteristics are all given. Okay, then in this case you are supposed to design the circuit when the diode is operating in forward bias condition, meaning in this case what you have to do is you need to find for the unknown parameter, unknown circuit parameter, in this case the R value, because R is not given, so you have to find for the R. Okay, then the second one is you need to determine the diode current as well as the diode RF value, okay, where V gamma is given as 0.65 volt. Okay, so the solution for this is in the next slide. Okay, so as you can see from the solution, as I mentioned just now, for the design circuit, actually you are supposed to find for the missing parameter, okay, which is R in this case. Okay, you can get it from the KVL equation actually. Okay, then if you get from the load line graph just now, you can see that 5 over RR, okay, sorry, 5 over R is actually 2.5 milliampere from the graph. You can check. Then from here you can simply get R equals 2 kilo ohm. Okay, then for the second question, when you are supposed to find for the diode current and as well as the resistance value RF. Okay, so in this case again from the graph you know that at VD equals 0.7 volt, you substitute, you get ID at this value. Okay, then once you know the ID, once you know the VD and V gamma is given, obviously from here you can find for the RF value. Okay, so again, although the solution is given, you try to do on your own to see whether you really understand or not. Okay, let's recall what you should understand in this video. We already discussed two subtopics. The first one is on the diode DC analysis. Remember the three models. And the second one is on DC load line. Okay, the load line analysis. Okay, so that's all about this video. Thank you so much. Okay, my message to you guys is let's amplify the goodness around us and rectify our mistakes through Islamic electronification of our lives. Okay, so whenever you learn electronics, you also should see from the Islamic perspective so that we can somehow increase the goodness and stay away from the bad things. Okay, thank you so much. Bye.